Okay, so today we are going to have a look at the phase diagrams. There are binary phase diagrams, there are tertiary phase diagrams. We are going to have a look at the binary phase diagrams. Now, what are the phase diagrams? A diagram showing different phases at different temperature. It's a graph between y-axis and x-axis, where on the y-axis is always the temperature, on x-axis is always the composition. On x-axis, sometimes there are two x-axis. One x-axis at the bottom, one axis on the top. At the bottom, it's a composition by mass or by weight. On the top, it's a composition by volume. So composition by volume is different than the composition by mass. Now we are going to have a look at only binary phase diagrams. Now what are the binary phase diagrams? Binary phase diagrams are the phase diagrams between two elements, two alloying elements. So for example, the one we will investigate is the iron-carbon diagram. So we call iron-carbon diagram, which is the binary phase diagram between an iron and a carbon. So that should be iron and then another iron-carbon diagram. Okay. Now then there is a thing called an important point known as the triple point. Now the triple point is a point where all three different phases coexist. So a solid, liquid and a gas, all these phases coexist at the same temperature. It's to do with the temperature and the pressure and the whole external conditions. Now, if we have a look at here, that line on the top, you're not able to see. Oh, you're not able to see. That line on the top is liquidus line. The very top line. Now here, if you have a look at that one, this diagram, this line over here is known as the solid liquidus line. This line. Now the reason this line is called the liquidus line is because above this line everything is liquid. Then there is another line, which is this line. Below this line, everything is solid and is called the solidus line. In between, it's a mixture of liquid and solid.
Is this any material?
It's just a generic phase diagram, but every material has its own phase diagram. On this axis, there is 100% A. So it's pure A. On this axis, it's 100% pure B. Now there is a metallurgical rule. The metallurgical rule states that if you add the impurity into any element, the melting point of that element decreases. It's a metallurgical rule that melting point of a pure metal is always higher than its alloys. For example, if you got like aluminium, the melting point is 660. The iron, the melting point is around 1380 or 1480, something like that. If you add 90% aluminium plus 10% iron, the melting point will be less than 660. If you add 90% iron plus 10% aluminium, melting point will be less than 1380. This makes sense. Yeah, this makes sense. But that one doesn't make sense. Even though the melting point of the iron is a lot higher and you're adding something of a high melting point, it should increase. It does not. Why? Why it does not increase? Because there's a lot of other things happening. When you add the aluminium, it kind of either go into interstitial spaces or substitutional spaces in a crystal structure, which actually affects the bonding because it supplies some forces, and the melting point is nothing but breaking these bonding forces. So sometimes it increases the bonding forces, sometimes it decreases. So in this case, it decreased the bonding forces and hence decreased the melting point. Now, if you have a look at here, you can actually see if you have a look at here, you can actually see as I'm adding the this is, let's call this one as alpha phase, and let's call this one as beta phase. Yeah, so alpha and beta, there are two different phases in there. As I'm increasing the composition of B into A, the melting point is kind of decreasing and decreasing. It will start increasing here for some other reason. We'll talk about that one. Now, how do we find out what is at any specific point? For example, I want to find out what is here. If I want to find out what is here, it's a liquid because it touches the liquidus line, and here it's a beta. So liquid plus a beta, they are any phase, but we'll talk about the iron carbon later, and then I will explain a bit more. Here I want to find out here, it's an alpha because this is an alpha phase, and a beta. This thing is more closer to the beta, so there is more beta than alpha. Yeah, okay. Now
where the yellow dot is in the middle.
I want to record what's here, and here I know it's pure alpha. Now we're not considering it's iron on carbon, we are just imagining it's in phase called pure alpha. When I look at the structure of, let's say, is alpha will look something like that. It will have nothing else but a pure grains of alpha. This is a one grain of alpha, other grain of alpha. The black lines are known as grain boundaries. Now, if I want to move here, I want to find out what's here. This is at alpha plus liquid. So alpha plus liquid. So here, the white ones are the alpha and the black background is the liquid. So this is how the microstructure will look like when you look under microscope. So there is a lumps of alpha solidifying. If you decrease the temperature, the alpha, these white thing will increase and the black will decrease. Now, if you further move towards that one, this line, because now it's more closer to the liquidus line, this point. So which means there will be more liquid. As you can see here, there is more liquid and less alpha. So the white bits are less and they are more black liquid. The liquid, alpha and beta. Now if I go here in the middle here, this is nothing but because it's above the liquidus line. So the only phase that exists here is liquid. Here you can see black liquid, just like that. Now, if I move here, then that will be a beta plus a liquid, and the microstructure will look like that. The gray things are the beta, the black is the liquid. If I move from here, this point to that point, what will actually happen is there will be more of the beta and less of the liquid. So the beta has increased, as you can actually see. If I enter into this region only have the beta. So then we will have the crystal structure. These are crystals of beta with the crystal, these are grain boundaries. The size of these crystal can be small and bigger depending on what crystal it is. Now, let's have a look at the bottom here at this point. At this point, there is a composition of alpha plus a beta. It's an alpha beta composition. At this temperature and composition, the microstructure consists of a grain of pure alpha plus a pure beta. Because this is more closer to the alpha side, which means it will have more alpha than a beta. There is an equation, Lever rule. We can use that rule to actually find the exact composition of alpha and beta. How many percentage alpha, how many percentage beta. Now, let's see if I move towards the right and what happened. As I move towards the right, you can actually see here there was a lot of alpha, the white ones. As I move towards the right, you can see the amount of the white, which is an alpha, start to decrease, but amount of the gray will start to increase. It's still a pure alpha and a pure beta. They have a laminar structures like a line. Okay. Now, what is eutectic and eutectoid mixture? I will explain that one in a minute with the iron carbon phase diagram. Okay. Now, let's say as I move here in the middle, here, this is known as the eutectic composition. Now, what is a eutectic reaction? Eutectic reaction is a reaction when the liquid start to cool. So imagine this is a liquid. It's still liquid here. It's still liquid here. I'm just decreasing the temperature. When it starts to cool, at a specific point, a reaction happens. That a liquid converts into two types of solid. One liquid converts into two types of solid, solid 1 and solid 2. These solid 1 and solid 2, if you heat them, if you increase the temperature, will convert it back into the liquid. So this reaction is known as eutectic reaction. There's another reaction, eutectoid reaction. We'll talk about that one later. Okay. Now, if I move forward, the amount of the alpha is decreasing, but amount of the beta is increasing. Now here you can see the lot of beta, but very little white, which is an alpha. Yeah, and always the structure will be laminar. You can find the percentage of that one. Okay. In this diagram, this is the iron, copper and nickel phase diagram. Now, this one is a copper and nickel phase diagram. At that, you got 100% pure copper, and on this, you got 100% pure nickel. As you move toward this side, the composition of the nickel increases. As you move this side, the composition of as you move this side, the composition of the nickel decreases. As you move this side, the composition of the copper decreases. So copper here is 100%. Yeah. Here the nickel is 20%, and this is by weight. Now, if you have a look on the top, this is also the composition by weight, by volume on the top. So we look at the bottom one. See, oh no, luckily this is same, but on the top sometimes it's different. It's by volume, but because they are matching together, so they have the same composition. So now if you have a look at that one, this is the liquidus. On this side there is a temperature. This is the liquidus line, the top line, and this one is the solidus line. Below everything is solid. Now there is only one phase, which is, they call it alpha phase. The alpha is a mixture of copper and nickel. Now if we want to find out, here in the middle it's a alpha plus a liquid, because they will be liquid and alpha. If I want to find out what is there at that specific point, I will use a rule called Lever rule, and I will just draw a point straight from this black spot all the way down, and where is touching this line on the top all the way down, and that line where is touching that line all the way down. And I will record these values, whatever these values are. This is 40 plus something. Let's call it, let's say it's 45, and let's call it 37 or 32. I think on the next slide they have the values. So 32, and this is 45, and this one is 35. Once I got this one, what I can actually do is I can actually use, I got 32% nickel, 35% nickel, and 45% nickel. As you move towards this side, there is more alpha. As you move towards that side, there is more beta. Now let's have a look at that one. If the temperature is 1300, there is all liquid. When the temperature is less than 1300, 1250, there will be a liquid plus a mixture of solid. The solid will have copper and nickel. The liquid will have copper and nickel. And at that temperature, 1200, everything will be